So let's look at some PNP transistor amplifiers. We're going to look at common collector, common emitter, and common base. And then I'll show you some situations where a PNP amplifier might be worthwhile. Normally you'd want to use an NPN. So in this video, we're only going to be looking at PNP amplifiers. Let's go ahead and get started here with example 1. This is an example of a common collector amplifier, and I can tell that it's common collector because the collector here is grounded. It's attached to the common, or the ground. Therefore, it's common collector. Let's review what my expectations are for a common collector transistor amplifier. Well, we expect the input impedance to be high. We expect the output impedance to be low, and we expect the gain to be approximately equal to 1. And all these things will be true provided that the amplifier has a reasonable design. That is to say, it has to be properly biased in the forward active region with reasonable choices for the capacitor and resistor values around it. Let's first do a DC bias check before we calculate the gain. Let's start with the base voltage. It's going to be determined by the voltage divider set up by the 8 kilo ohm and 10 kilo ohm resistors. That works out to 5.56 volts here. We can then find the emitter voltage because it should be 0.7 volts higher than our base voltage. Our voltage here at the emitter works out to be 6.26 volts. The emitter current, I sub E, is then the voltage drop across this 1 kilo ohm resistor divided by 1 kilo ohm. So we have 10 at the top of the resistor and 6.26 at the bottom. We get about 3.74 milliamps here, and that current's basically going to flow through the collector, which is just grounded. We'll have a little emitter resistance right here, and I could label it R sub E. You might recall that that little R sub E can be determined by taking 26 and dividing it by our emitter current expressed in milliamps. This formula works at room temperature, and here it works out to be 7 ohms. It's negligible when you compare it to the 1 kilo ohm resistor, so we're basically going to neglect it here in this problem. Now for the AC analysis, we need to know what our input impedance Rn is. By inspection, I can see that it's 8 kilo ohms in parallel with 10 kilo ohms, in parallel with whatever I have looking into the base of that transistor. Looking into the base of a transistor, I've got quite a lot of resistance, and that's going to be multiplied by beta when I use impedance reflection. In other words, I'm going to have beta times R sub E plus 1 kilo ohm from the emitter resistor in parallel with my 500 ohm load. However, because this is such a large number, I just want to neglect it here. Our emitter resistance here works out to be about 4.4 kilo ohm. Let's now draw our small signal equivalent circuit. First we have our source, and then we have our 100 ohm source impedance, then we have Rn. In this case, Rn, again, is 4.4 kilo ohms. For a common collector amplifier, the voltage gain is just 1, so I'm going to label that 1. We have to imagine in a way that the source sits right here at the emitter on one side of the emitter resistance. There's the emitter resistance, and then from the perspective of the AC signal, we have 1 kilo ohm to ground and 500 ohms also to ground. My load is determined by the ratio of the output voltage to the signal voltage. So we have 3 determining sections, or 3 parts of our equation for finding the gain. We have our input voltage divider, we have our gain segment, and then we have our output voltage divider. Our voltage divider from the input stage is just 4.4 kilo ohms divided by 100 plus 4.4 kilo ohms. Our gain stage is just 1 copied from the source. And then here we have a ratio that's very close to 1. This number is 0.98. This ratio is also roughly 0.98. So taken together, we have a gain for this circuit of about 0.96. I started off the problem by just looking at it and saying, oh, it's a common collector amplifier. The gain is probably about 1. And that was a reasonably good approximation in this case. And the reason it worked so well just by looking at it is because it was a reasonable design. Let's now look at an example of a common emitter amplifier. I can tell that it's a common emitter amplifier because the emitter is up here where I see the arrow, and it's connected to the power supply. It's not connected to either the input or the output. All of the equations for dealing with these amplifiers for the PNP transistor are identical to those for the NPN transistor, as long as you can keep the collector and the emitter straight. The expression for the gain of a common emitter amplifier after you've dealt with the input stage is basically just the resistance seen from the collector divided by the resistance seen from the emitter. With NPN transistors, we're used to seeing the collector resistor up here and saying this resistor divided by this resistor gives us the gain. But here you have to invert it, right? Because the collector's at the bottom. So if I just look at these two resistors, I can say, well, the gain is going to be about negative 1.1 divided by 1. And then we have to modify that by the input and output impedances. Let's go ahead and fully analyze the circuit. And I'm going to start with a DC bias check. Let's label our base voltage, and it's going to be determined by the voltage divider set up by the 10 kilo ohm and 8 kilo ohm resistors. It's going to be some fraction of 10 volts. In this case, it works out to be 5.6 volts. The emitter voltage should be higher than that by about 0.7 volts. 6.3 volts. We can then find our emitter current, I sub E. It's the voltage drop across that resistor divided by the resistance. The 3.7 milliamps then flows through the 1.1 kilo ohm resistor. The collector voltage is just Ohm's law applied to the 1.1 kilo ohm resistor. Let's do a quick check of our voltages. Is our emitter voltage higher than our base voltage? And that should be higher than our collector voltage? It looks to be okay in this problem, right? We have the high voltages at the top, and then the voltages progress lower and lower as we read down the circuit diagram. That's a good indication that this transistor is in the forward active mode. The base current is probably negligible as well, simply because we have about a factor of 10 between the resistors at the left and the resistors at the right. And I'm not going to bother to prove that it's negligible here. Let's go ahead with our AC analysis now. For that, we're going to need expressions for the input impedance and the output impedance. The input impedance is just 8 kilo ohms in parallel with 10 kilo ohms in parallel with the resistance looking into the base of that transistor. We'll have to use impedance reflection to move the resistances at the emitter over to the base side by multiplying them times beta. Since this is 1 kilo ohm here in the equation, and we're going to be multiplying it times a large number beta, 100 or so, I can see that this is a pretty large number, so putting it in parallel with 8 kilo ohms or 10 kilo ohms is not going to make much of a difference. So let's go ahead and neglect this term, and I won't bother calculating R sub E either. Our input impedance then is just 4.4 kilo ohms. We can find our output impedance by inspection. It's just 1.1 kilo ohms. And looking up into the collector is basically looking into a current source. The impedance is so large that I can just ignore it. We then have enough information to make our small signal circuit. First we have our source impedance, and now we have our input impedance. Now for our gain segment, we have to recall the gain of a common emitter amplifier. It's negative the collector resistance divided by the emitter resistance. And then the rest of our circuit is just our output impedance and our load. We can label our output voltage and find an expression for the net gain. We're going to have an input voltage divider, our gain expression, and then our output voltage divider. And before I calculate that out, I just want to point out that all of these numbers taken together is the load resistor in parallel with the collector resistance. If we look at our expression for the gain over here, an expression that's easy to remember, we can see that indeed we have the resistance at the collector divided by the resistance at the emitter right here. Our input divider gives us 0.97, our gain is minus 1.1, and our output divider is 0.45. Overall, we have a gain of about -1/2. Not too bad, but what would you do to the circuit if you wanted a higher gain? Well, the easiest way to increase the gain is to reduce the resistance at the emitter. It's down here in the denominator, so we should make this resistor a little bit smaller. And we can do that effectively by adding a capacitor there next to it so that we don't change the DC bias points. That's what we're going to do in example 3. Example 3 is identical to example 2 with the exception of this branch in parallel with the emitter resistor. If we were to apply impedance reflection in order to calculate the resistance looking into the base of that transistor, let me call it our pi, then we would find that the new emitter resistance, this 1 kiloohm, is going to modify that just a little bit. Let's find an expression for it, and I'll call this RE right here. Our emitter resistance here, I'll also label little re. Our pi is then beta times RE, which is in series with these two resistors in parallel. If RE1 is too low, then it starts to make R pi lower and lower, which starts to affect our input impedance looking into the transistor. In this case, though, RE in parallel with RE1 is just going to give us 500 ohms. When we multiply that times a beta of 100 or so, we get something like 50 kiloohms. So I'm not going to worry about putting that in parallel with our 10 kiloohms and our 8 kiloohms here when I calculate the input impedance. Let's just use our value from the last example, 4.4 kiloohms. Our output impedance is also unchanged from the previous example, and we can also see by inspection that it's just 1.1 kiloohms. Let's draw the AC equivalent circuit. We have our source, our 100 ohm source impedance, and then our input impedance. We then have our gain, and our gain for a common emitter amplifier is negative the resistance looking at the collector, which in this case is 1.1 kiloohms, divided by our resistance looking out of the emitter, and I'm going to neglect little r sub e and just write 500 ohms, 1 kiloohm in parallel with 1 kiloohm. This is our output impedance, which is 1.1 kiloohm, and then finally we have our load. Let me label our output voltage, and we can go ahead and write an expression for the overall gain. We'll have our expression for the input voltage divider, our gain, and our output voltage divider. We have a voltage divider at the input that gives us almost 1. That's good news. A gain of -2.2, and kind of a poor output voltage divider of 0.45. Our overall gain, though, is 0.97, about twice what it was in the last problem. Since we've taken our emitter resistance and effectively used half the value, that's exactly the effect on the gain that we expect should happen. Let's try to make the gain as large as possible by putting a capacitor across the entire emitter resistance. In this case, our little r sub e is no longer going to be negligible. Let's first find our DC bias points. The voltage divider, or the DC analysis, is no different than it was in example 2. So I'm just going to copy the values for the base voltage, the collector voltage, and the emitter voltage. I'll also label my emitter current, the DC emitter current that is, and we also found that in a previous example, so I'm not going to go through that calculation again. What we are going to need in this example is little emitter resistance R sub E, and we can find it by taking 26 divided by our emitter current, expressed in milliamps, which gives us 7 ohms at room temperature. If we want to know our impedance looking into the base of a transistor, R pi, we can just take RE and multiply it times beta. We can't neglect R pi this time because the number is too low, so let's recalculate our emitter resistance. Our emitter resistance is going to be 8 kiloohms from this branch up here in parallel with the 10 kiloohm branch down here, and that's going to be in parallel with R pi, which in this case is too small to neglect. We wind up with about 600 ohms here for the net input impedance. Our output impedance over here is just what it was in the previous examples, 1.1 kiloohms. We now have enough information to proceed to the AC analysis. We have our signal, our source impedance of 100 ohms, our input impedance of 605 ohms. Now we have our gain for a common emitter amplifier. It should be our resistance at the collector divided by our resistance looking up the emitter. So here we have 1.1 kiloohms for the collector, and then for the emitter we have only little r sub e because this is effectively grounded. This is a really big number, and this is about as well as we can do here for the gain of a common emitter amplifier. Our output impedance here is 1.1 kiloohms, and let's go ahead and draw in our load, which is still 900 ohms. Labeling our output voltage, we can then find an expression for the overall gain of this circuit. The input impedance is a little bit reduced compared to what it was in the previous examples. Numerically, it works out to 0.86. You might recall that when we didn't have this capacitor bypassing the emitter resistor, this number was a lot closer to 1. Here our gain is minus 157, which is about the best you can do. And then we have our output voltage divider. It's unchanged from the previous example, and our net gain winds up to be negative 61. Now, a gain of 61 is a pretty decent gain, and the reason why the gain in this example could be so high is because our load resistor is not really all that small, 900 ohms, so we can get a fairly respectable gain here. One thing I should point out is that this 61 is probably not a very predictable gain. We know because it depends on little r sub e that it's going to change a little bit with temperature. So if you need gain that's really predictable, you have to use other methods to get it. For example, negative feedback. That wraps it up for the common emitter, but now I'd like to look at an example of a common base amplifier made with a PNP transistor. We can immediately see that it's common base because the base is attached to the common or the ground through that 1 microfarad capacitor. Let's start off as we did in the previous examples with the DC bias check. Our AC base voltage is always 0 because it's grounded, but we are going to have a fixed DC voltage at the base given by the voltage divider set up by the 16 kiloohm and 18 kiloohm resistors. Now that we know the base voltage, we can add 0.7 to it by assuming that the transistor is on and calculate our emitter voltage. We find 8.2 volts, and it's still lower than 10 volts, which means that current is flowing in the correct direction through this emitter resistor. Let's go ahead and find the current. We have 10 volts at the top and V sub E at the bottom, so that gives us the voltage drop. The resistance is 1 kilo ohm. So using Ohm's law, we have 1.8 milliamps of current flowing through that resistor. If we assume that that current flows also through this collector resistor, we have enough information to find the collector voltage. We'll assume that our collector current is nearly equal to our emitter current, and we know what resistor is attached to the collector. This gives us 2.2 volts. I can see that the transistor is properly biased in the forward active mode because we have the higher voltages at the top, medium voltages in the middle, and then lower voltages down towards the bottom of the diagram. So the arrow is pointed in the right direction for forward active mode operation. I can also see from the values of the resistors that it's very likely the base current is negligible in this case. For our AC analysis, we're going to need a value for little r sub e, so we can go ahead and calculate it since we know the emitter current. It works out to be about 14 ohms. Let's go ahead with our AC analysis. I'll start off by drawing the source, and we kind of have to unwrap the circuit because we have the signal running from right to left, down through the transistor, and then left to right. So I'm going to unwrap it and draw everything from left to right. So we'll start here with V sub S, which is attached to a 10 ohm resistor. Our input impedance here is going to be 1 kilo ohm from the top branch, and that's going to be in parallel with R sub E from the branch going into the transistor. There's no need to use impedance reflection to bring resistances over to the emitter side because the base is just grounded. So if you reflect a ground, it's still a ground. That wraps it up for the input voltage divider. Now we have our gain diamond. For a common base amplifier, it's the resistance at the collector divided by the resistance at the emitter, but you have to be very careful about which emitter resistance you're talking about. The collector side is easy. This is R sub C right here. For our emitter side, we're only going to be including R sub E. Our output voltage here is just 1.2 kilo ohms, and then we finally have our load. If you want to include the full emitter resistor down here in the denominator, then you can include R sub E in parallel with R sub S. That is, you can get everything in that expression. But if you do that, then you need to neglect to include R sub E over here on the left. You'll wind up with the same answer. Now that we have our small signal diagram, we can find an expression for the overall voltage gain. We have a voltage divider here at the input side. We then have a very large gain here at the diamond, and then we have an output voltage divider as well. We'll use about half of our signal at the input side. We definitely make up for it with the large gain, and then we lose some of our signal again at the output side. But overall, the gain is a very reasonable value in this particular example. One thing about the common base configuration overall is that it is sensitive to temperature because of this dependence on R sub E. So it's something to keep in mind when you're designing circuits. Of course, all of the circuits that I've just worked out could have been implemented with NPN transistors, and that probably would have been better. The advantage of using a PNP transistor from time to time comes when you want to cascade stages together. I'm going to show you one of these applications. So I'm going to start with 2 NPN transistors. Let's calculate the gain, and then I'll show how you can improve the situation by substituting one of the NPN transistors with a PNP transistor. You might notice that we have 2 common emitter amplifiers. I can tell that they're common emitters because the emitters are not connected to either the input or the output in either amplifier. You see, the signal enters at the base and exits at the collector, and again with the other amplifier. You might notice something about these cascading stages, and that is we have a lot of resistors in the middle. The voltage at the collector of transistor number 1 has to be a little bit higher than the voltage at the base of transistor number 2. This is called level shifting. We need to make sure that the DC averages of all the signals are right in the middle so that the signal can swing up and down without either causing the transistor to go into cutoff or saturation. Doing this level shifting, though, requires a capacitor and some resistors to provide the appropriate bias points. This is something that we're going to remedy by changing something to a PNP transistor. But first, let's calculate the gain of the circuit as we see it right now. These two amplifiers are identical except for the input and output sides. So let's do a DC analysis that covers both. The base voltages are going to be equal, as will be the collector voltages and the emitter voltages. The base voltage is going to be some fraction of the power supply voltage, and that fraction is going to depend on this 12 kilo ohm and 8 kilo ohm resistor. Now we wind up with 4 volts at the base. Why isn't it 5 volts? Wouldn't 5 volts be better? Isn't that right in the middle of the power supply and ground? Well, in this situation, it's actually better to have the base voltage a little bit lower than the halfway point because the signal's not yet amplified there. The amplified signal comes out of the collector, so that's normally where you want the signal to have a lot of room to swing around, where it's already amplified. So having the base voltage a little bit below the midway point is usually advantageous. The emitter voltage for both of these amplifiers is going to be 0.7 volts below the base voltage. We wind up with 3.3 volts. The emitter current is only going to be flowing through the 1 kilo ohm resistor. It works out to just 3.3 milliamps then. That same current flows through the 1 kilo ohm collector resistor, and that allows us to find the collector voltage. Before I go on to the AC analysis, I just want to point out what would happen if we didn't have this capacitor right here and we didn't have these two resistors. If we didn't have them, then I would label this VB2, the base voltage for transistor 2. If that equals the collector voltage for transistor 1, then my emitter voltage for transistor number 2 would be 6 volts. This means that my emitter current for transistor number 2 would be 6 milliamps. My collector voltage would then be 10 minus 6 milliamps times the 1 kilo ohm collector resistor. That would be 4 volts. But look what's gone wrong. The collector at 4 volts is lower than my base voltage. That's impossible. This transistor would be in saturation. Our first amplifier would be absolutely fine, transistor number 1, but we can't just cascade these transistors without the biasing network because then transistor number 2 would be in saturation. With that in mind, let's go ahead and calculate the gain since we know it's going to be okay. Let's find our emitter resistances, little r sub e, and they're going to be the same. I know they're the same because my emitter currents are the same. It works out to 8 ohms in this example. Let's then find our expression for R pi, the resistance looking into the base. In this case, it's going to be beta times all of the resistance attached on the emitter side, which in this problem is 1 kilo ohm in parallel with 200 ohms. So for the resistance looking into the base of the transistor, we get 17.5 kilo ohms. Let's label the input impedances, which will also be the same. It's 8 kilo ohms from the branch to ground in parallel with 12 kilo ohms, the branch up to the power supply, in parallel with R pi. By the way, my use here of R pi is not standard. R pi is usually defined as beta times little r sub e, and here I'm using it for the full base resistance. Just something to keep in mind. I'm consistent here in this problem, though. The input impedance winds up to be 3.8 kilo ohms. The output impedance is just 1 kilo ohm by inspection. The output impedance up here is also 1 kilo ohm. We can now draw our small signal equivalent circuit. We have our signal impedance, 100 ohms, and then we have our impedance looking into the first amplifier, 3.8 kilo ohms. This is a common emitter amplifier right here. The expression for the gain here will be the resistance at the collector divided by the resistance at the emitter. I'm going to neglect little r sub e because it's so much smaller than the others. We now have our output impedance from the first amplifier. It's 1 kilo ohm, and then that's connected to the input impedance of the next stage. We have another common emitter amplifier, and the gain is the same as what it was with the first one because we have the same resistors in place. Finally, we have our output impedance, 1 kilo ohm, and our load. Let's label our load voltage, and we have everything we need to write a full expression for the gain. First, we have our input voltage divider, the gain of our first amplifier, our output stage of the first amplifier, and our input stage to the second amplifier. It's all in this one expression. Our gain for the second amplifier, and then finally our output stage of the second amplifier. We have a nice high input impedance, so we get a number very close to 1 there. Our gains are -6. We lose about 4/5 of our signal here between the amplifiers due to the resistors creating the bias network, and then we lose half of our signal here at the load. Overall, our gain is a positive 13.7. 13.7 is not too bad, but I'm going to show you how you can both improve the gain and get rid of some of the components all at the same time by using a PNP transistor for stage 2. The problem if we make the base voltage for amplifier number 2 equal to the collector voltage for amplifier number 1 is that the base voltage might be too high. That's what we want if it's a PNP transistor instead of an NPN transistor. Here's what we're going to do. We've gotten rid of the capacitor and 2 resistors at the same time. Some of the expressions are the same as they were before. I'm going to label those first. Let's call this Rn1, the input impedance to the first amplifier. It's still 3.8 kilo ohms. Nothing's changed. However, Rn2 is improved. It's improved because we no longer have a 12 kilo ohm branch and an 8 kilo ohm branch right here. It's just what I was calling Rpi, or 17.5 kilo ohms. It's improved, so our gain's going to be a little bit better. Because I've reversed the collector and the emitter positions, there's going to be no problem with the DC voltages, and it's going to be in the forward active mode. Our output impedance here is 1 kilo ohm, just like it was before, and our output impedance of amplifier number 2 is also 1 kilo ohm. Let's go ahead and write an expression for the overall gain without drawing the small signal circuit model. We're going to have a voltage divider here at the input side, just like we did before. We'll then have our expression for the gain, which is also unchanged. It's just this resistor divided by these 2 resistors. We then have a voltage divider set up by Rn2 and Rout1. We again have gain of a common emitter amplifier. You just have to remember that the collector is now down here and the emitter is now up here. The numbers are the same though. And we finally have our load, which is the same voltage divider it was before. The load is still connected to the collector, it's just down here instead of up here. This is exactly what it was before, this is what it was before, and this is what it was before. This number is 0.95 now, whereas before it was 0.79. So we've made a little bit of improvement to our gain, but we've also used fewer components. No capacitor and no bias network right in between those 2 stages. Our net gain here works out to be 16.5. I simulated it on LT Spice and it came out to be 14.7, so not too bad. The main idea here is that you can sometimes use PNP transistors to get rid of some of your components. In the next video, we're going to look at another way to combine transistors, but they're going to be the same transistor. We're going to be looking at the Darlington configuration next.